Okay, so I'd like to talk about slip in hexagonal close-packed materials, zirconium specifically. I'll very quickly go through the main slip modes that occur in the material. So let's start with our ball model here, and what I've got here is hexagonal structure. It's the same one I used to demonstrate twinning. We have the basal plane here and the prism plane shown here. It's corrugated. And if one was slipping on the basal plane, although basal slip is not very commonly observed in zirconium, in fact, I don't think there's quite a bit of controversy about whether it happens because of the C/A ratio, because of the anisotropy of the zirconium matrix. What you have is if there was slip on the basal plane, it would occur by shearing on this plane. So the shear involves two partials, which are a third 10-bar-10 Burgers vectors. So we have one partial, two partials. And then if we want to do it again, one partial, two partials. And then again, one partial, two partials. And that brings each pair of partials of 1/3 10-bar-10 constitute the 1/3 11-bar-2, and that brings the material back into conjunction in each case. Now, because hexagonal zirconium has a C/A ratio which is less than ideal, about 1.59, what that means is the prism planes, these planes, are actually the mostly higher density of packing of atoms, and so you don't get as much activity on the basal plane as you would for something like zinc and cadmium. So that means that there are two other planes which are more prominent when it comes to deformation in hexagonals in zirconium, and that is the prism plane, which is this one. And if I were to demonstrate prism slip in the A direction, which is the commonest, the smallest dislocation, the Burgers vector, A slip involves just simply moving one row of atoms relative to another, or one plane of atoms relative to the other. There's a very slight partial involved, but it's such a low energy intermediate state that there's very little observation of that splitting of the dislocations, giving you that from that to that partial configuration is very rarely observed, and often you just see simply the A slip occurring. If we're on the prism plane, pyramidal plane, which is this one, this is my basal plane, and this is now the plane which is inclined like this to the basal plane. It's inclined this direction. You can have prism slip also on the pyramidal plane, and there is no intermediate partial site for the atoms to sit. So so when you have A slip on the prism plane, it's just there is no splitting, there's no partial intermediate steps. Now, when it comes to displacements which are perpendicular to the basal plane, inclined to the basal plane, we'll go back to the prism planes, these corrugated prism planes. Because of the corrugation, it's very difficult to displace the atom, to shear one plane of atoms in that direction, perpendicular to the basal plane. It's just not going to happen. You'll get A slip very easily on the prism plane, but you basically you don't get any action in the non-basal direction. So in directions inclined to the basal plane. However, for pyramidal planes, it is possible to get what's called C plus A slip, and there are three intermediate partial positions, 1, 2, 3. So in going from this position to this position, from here to here, involves three partials. The first one is 1/9, 1/1/3. The next one is 2/643 type thing, and then the last one is a 6/2 or /2/3. So we end up with that possibility, and in fact, when you do get deformation inclined to the basal plane, it typically happens on these pyramidal planes, because you have this potential for easy slip. And because you have the partials, that then leads you to another mode of deformation, which is twinning. That allows, because you have these partial intermediate stages, then that means that this plane is a potential twinning plane. And I talk about that in other videos.